Dear friends, this is the time when we are ready to make authority command on configuration of D2 ion in a large splitting. This splitting actually is very important in making coordination diagrams, which we also call as the Tanabe-Sugano diagram. The configuration of D2 ion in a large splitting would possibly give us three combinations. So in the limit of extremely large splitting of d orbitals, the configuration that are possible are this in terms of increasing energy. So either T2G2 or T2G1, EG1 or EG2 describes as the electron in T2G2 are the two electrons distributed into two set of d orbitals, that is the ground states, or possibly the one electron in the ground state and one electron in the excited state, so T2G1 and EG1, or both the electrons in the excited state. So this would be in fact a very limiting case with a very high value of EG2 system, and therefore we are now ready to understand the various configurations and the terms that are associated with that. So let's begin with configuration of T2G type. Now here, both the electrons may occupy the stable T2G orbitals, and their direct product would come from the character table for the octahedral point group, that is OH point group. And this configuration, when we are saying that it is T2G2, it means that you are multiplying T2G with 2 T2G, giving rise to these values, that is 3 into 3 is 9, 0 into 0 is 0, 1 into 1 is 1, minus 1 would give plus 1, minus 1 and 1 here again. 3 square is 9, minus 1 square is plus 1. Similarly, 0 square is 0, minus 1 is squaring gives plus 1, and 1 is 1. So we have obtained a set of reducible representations just by direct product of the two representations that we see, T2G into T2G. Now it is quite easy to see that this can be decomposed into the terms A1G, EG, T1G and T2G from the character table using our standard reduction formula. So these are the corresponding group theoretical terms related to T2G and T2G configuration. For this, it can also be referred to the character table and can be seen that this total falls into T2G into T2. That means if you are talking about 3 into 3, because it is 3-dimensional and 3-dimensional, so there are 9 such possibilities. So 1 plus 2, E stands for 2, plus 3, T is 3, then again 3, so 3 to the 6, plus 2, 8, and 1, 9. So there are 9 combinations are the product of these T2G and T2G product. So further, when we are now looking for the extreme case where the electron is present in either T2G or EG, one electron is present in both of the orbitals, is one electron in T2G and one electron in EG. This is a possible combination, and again we'll go for the direct product of representations giving rise to what we know as the character table. Just we have seen that the EG and T2G lines have been mentioned in the character table, and we have simply to go for the direct product of these representations. So there's 3 to the 6, 0 into minus 1 becomes 0, 0 into 1 into 0 becomes 0, minus 1 into 0 becomes 0, and so on. So if we keep on multiplying the two terms, and so we are getting what we are is T2G into EG, that is 600, and so on. And because it does not belong to any of this character table, it is obvious that this has to be a reducible configuration, and the direct product of this would yield, when we are using the standard reduction formula, that T2G into EG has to be something like T1G and T2G. Now again, because this is 3 and this is 2, so 3 into 2 is 6. That would be facilitated by 3 plus 3, that is T1G plus 3 T2G, and this is how it can be inspected from the character table also. Now at the extreme end, we are left with both the electrons that are occupying into the EG level. Now this is the possibility when there is a extremely strong field. Both the electrons are there in EG orbitals. The direct product of EG and EG, that's going to obviously yield the values that have been shown here There is 4 1 0 0 4 4 0 1 4 0. Obviously, you can understand that it has been squared the value, and because 4 is not coming into any of the part of the character table, it can be further decomposed to give the configuration that is something like EG into EG, that is A1G plus A2G plus EG. So what we are left is two-dimensional 2, that's 4, that comprises to give A1G. That reducible representation goes to irreducible components like first order, first dimension and two dimension. So 1 plus 1 plus 2, that yields 4. You can further check by observing the character table also. So now we have these three combinations of orbitals, and the direct product have given the answers to these products. So T2G into T2G, that is this possibility where T2G, both the electrons are present in T2G orbital, that is dz square and dx square minus y square. In another case, T2G and EG, T2G and EG would give T1G and T2G, and one electron is there in the ground state and one electron in excited state. And to the extreme level, EG2 configuration is possible where both the electrons are present in the excited state. Now, as we have seen, by decomposing the reducible representation into irreducible components, we have received these values. So for EG and EG, these values we have obtained are A1G, A2G, EG. So A1G, EG, and A2G that we have seen. But here what we are missing is the states, the multiplicity of the states are not being decided as yet. So microstates have not been decided so far. Similarly, when you are talking about T2G and EG1 configuration, that is going to yield T1G into T2G. But whether T1G and T2G are singlet or triplet or both, it has still not been decided from any of the calculations that we have done in the previous case. So the possibilities that have been shown here are 1 T1G, 1 T2G, 3 T1G, and 3 T2G. Now, how we have reached to this particular conclusion, that we have to further see. Similarly, when you are multiplying T2G and T2G, so A1G, EG, T1G, and T2G. So A1G, EG, T2G, and T1G. But we are still not sure about the multiplicity of the states of this particular configuration. So what to do to determine the microstate splitting patterns of this particular cases? We have yet to determine the spin multiplicity of these states clearly with two electrons involved. Because there are D2 system, they must have be either singlet or triplet. Both the electrons are paired or both the electrons are unpaired, and therefore there are only two possibilities, singlet or triplet, that has we must observe any restriction placed on multiplicity by the exclusion principle. Let us do one by one. Let's talk about T2G configuration. Now, when you are talking about a T2G2 kind of thing, what we are inferring is that there are three orbitals, that is dxy, dyz, dxz. In qualitative terms, they are the three d orbitals, degenerate orbitals. So there are altogether 6 orbitals we can assume with this, either spin is plus half or minus half. So what I suggest is the orbital degeneracy would be in this particular case 3, and the spin degeneracy is equal to 2. So the permutation or the combination factor suggests that factorial 6 upon factorial 2 into factorial 4, that is giving the 15 unique ways of assigning the values. And these 15 microstates are possible out of T2G configuration that has given A1G, EG, T1G, and T2G that we have seen in the previous section. So T2G into T2G has already given us this value, and we are not because sure about the multiplicity. Let us assume that their multiplicities are A, B, C, and D, as we know that they are either 1 or 3, singlet or triplet states. And there are 15 total degeneracy may be possible, and if you go logically, this combination of 1A plus 2B plus 3C plus 3D, so A, B, C, D values, and the summation should be 15. When we wish to identify these values, what we suggest that all of them are 1. This is ABC is equal to 1, but D is equal to 3. This is one of the possibility, although there are other possibilities as well. So if we are saying that ABC is 1 and D is 3, so 1 A1G, 1 E1G, and 1 T1G, and 3 T2G are the possibilities. The possibilities are 15, and there are of course 3 solutions. Either ABC or D has 113 values, or 1131 values, or 3311 values. But in that case, the 15 states are not going to be possible. So we are left with only the option with ABC equal to 1, D being equal to 3. And in such a case, this configuration would fortunately give us 1A1G plus 1EG plus 1T1G plus 3T2G. Now, you can examine this also, as this is the 3 into 3, there's a 9, but it has to be into the 15 microstage. So 1 plus 2 plus 3. So 1 plus 2 is 3 plus 3 is 6. And 3 into 3, because this is triplet state and this is T, threefold dimension, 3-dimension of representation. So this is 9. So 9 plus 6 is equal to 15. So thus it satisfies that all possibilities are like this only. So for this, spin multiplicities have been assigned as 1A1G, 1EG, 1T1G and 3T2G. Lastly, possibility for EG2 type of configuration, which is the possibility where you have dx square minus y square and dz square, because there are only two orbitals. Orbital degeneracy and spin degeneracy would be 2 in both the cases, and now there would be some factorial 4 upon factorial 2 into factorial 4 minus 2, that is 6 distinguishable ways are possible, and we may therefore write that Eg into Eg should be equal to something like this, that we have discovered from the direct product of representations. So you have A1G, A2G and Eg, they have been spread like this, and we are left with the problem to assign the values of A, B and C, and there are two possibilities, either it is 131 or 311, and if you are trying to satisfy that there are the microstates that are possible. So we have seen that there are 6 distributions, there are 6 microstates are possible. We have to assign the values in the way that they should give the 6 values. So it is either 131 or 311. So the most acceptable solution would be 1A1G plus 3A2G and 1E2G. Though there are other methods also to reach to this conclusion as well. But if you are considering this, you have 1A1G is 1, 3, 1 plus 3, 3 into 1, that is 3. So there's a 4 and plus 2, 6, because E stands for two-dimensional irreducible representation. So that satisfies the condition of 131, the multiplicities. This satisfies the 6 microstates that are possibly there. Now last case is for T2G and EG configuration, and for this there are possibilities that one electron is present into 3 set of degenerate orbitals dxy, dyz, dxz, where the orbital degeneracy is 3 and spin degeneracy is equal to 1, because there is only one electron. And similarly, the possible combination here would be equal to factorial 6 upon factorial 1 minus factorial 5. There are 6 unique possibilities are there, because one electron has to be placed in the 2 boxes. And if we talk about the EG set of orbitals, that is dx square minus y square and dz square, there is orbital degeneracy would be 2 and spin degeneracy would be 1. So the possibilities would be that 4 combinations in such a system would be possible, and total of 6 into 4, that is 24 possible unique arrangements are there. And in such a case, we need to have particular statement into mind, that we know that there is no possibility of 2 electrons being in the same box, so that for all arrangements the spins may be either paired or unpaired. Thus the T1G and T2G may be both, or rather both, singlet and triplets. And if we accept this idea, so T2G into EG may be equal to T1G plus T2G, that we have discovered from direct product. And now T2G EG may come in the form of 1T1G plus 3T1G plus 1T2G plus 3T2G, because these are possible. This state are singlet triplet. This is also a singlet triplet state possible. Now if you compute them, this is 3-dimensional, so 3, this is 3 into 3, this is 9, this is also 3 and this is 9. So there are 2 9s, so 9 to the 18 plus 3, 10, 18 plus 3, that is 19, 20 and 21 possible states. So 21 and further 3. So here is for 3, here is 9, 9 and 3 is 12, 12 plus 3, 15 and 15 plus 9 is 24. Thus it allows the unique combination of 24 microstates. Now we are all set to go for a correlation diagram where we can correlate the spectroscopic terms with the group theoretical terms for the splitting with the strong interaction. So we can correlate from extremely weak interaction to very strong interactions, in the manner that we have these now states which are now in their microstates or multiplicities that have been assigned. So for T2G, you have one A1G, one EG, one T2G, and three T1G. Remember that we have 1 plus 1, that is 2, 2 plus 1 is 3, and 3 plus 9, that is 15 possible arrangements are there here. Here 3 and 3, that is 3 to the 9 and 9 to the 18, 18 plus 6 more, there is 24. 24 possible arrangements are there with T2G and EG1. And for EG2, we have 1 plus 1 plus 1 plus 2 plus 3, that is the 6 possible arrangements are there. So we have been able to actually develop the idea of splitting a very strong environment or strong interaction for a D2 case in an octahedral environment. So that's it for now. Thanks for watching this video. And in the next video, we'll be talking about the constitution or the formation or the correlation diagram, which ultimately leads to the famous Tanabe-Sugano diagram. Thanks for watching again.